Great, it's recording now. So today, let's talk about section 4.3 logarithmic functions and section 4.4 graph of logarithmic functions. Yesterday, we studied exponential functions. They look like this, right? Some base raised to some exponent. And if I ask you this question, what should be 2 raised to the third power? What should be the answer for that based on what we did yesterday? 2 raised to the third power. Anybody in the chat? Great. Very good, Lucero. Very good, Jing. Just the number 8, right? Just the number 8, because 2 raised to the third power simply means multiply 2 times 2 times 2. That is just 8. Great. Now, knowing that this guy is just equal to 8, to answer this question, we use our knowledge of exponentials, right? Exponentials. Now, having this in mind, let me ask you this question now in reverse. 2 raised to what number should be equal to 8? So what is the number I have to put here on top of the number 2, so that when I raise this number 2 to that number, I should get 8? What should be the answer here for this question? Anyone in the chat based on the previous result? It's sort of the question in reverse, right? First, we said 2 to the third power equal 8. Now we say 2 raised to what number should be equal to 8 based on this result? And the hint should be, right? Look at the exponent, right? Look at the exponent here. Very good. Savannah, very good. You got it. Yeah, right. So if we look at this result, we look at, pay attention to the exponent, that is 3, 2 to the third power was 8. So if I'm looking for an exponent such that when I place it on top of this number 2, as a result, I get 8, that number should be just 3, right? So in order to answer this question, we use what mathematicians call logarithms. And it's basically the exponent to which you raise some base, in this case 2, to get some given number, in this case 8, right? So this guy is just 3. And the way mathematicians write this out is as follows. They will say log base 2 of the number 8 is equal to 3, okay? So it's just exponentiation in reverse, and therefore it's going to be a little bit tricky. So I will go over this section very slowly. I will give you a lot of examples and techniques so that this process will become natural eventually. All right, so mathematicians define this formally using the following fact. F of x, b to the x is a one-to-one function, right? Remember yesterday we explained that exponential functions, they come in 2 shapes, right? Increasing or decreasing, but in both shapes, when you apply the horizontal line test, they will pass the horizontal line test, so they are one-to-one functions. So they have an inverse function, right? They have an inverse that can be inverted. F of x is an inverse function. This inverse function is called the logarithmic function with base b. Logarithmic function with base b. It's the inverse function of this exponential function, right? And the formal definition here is for x greater than 0, b also greater than 0, the base, right? And b not equal to 1. Yesterday, we explained that the base cannot be 0, cannot be 1, right? But in addition to that, notice x, the input value, should be positive. I will explain to you that later. Now, log base b of x will be equal to y if and only if b to the y equal x. It comes from this exponential result, right? If b to the y is equal to x, this exponent y is called the log base b of x. Okay, now this function f of x equal log base b of x, read log base b of x, is the logarithmic function with base b, okay? Now, when you have this log, two components are important. This component we said is going to be called the base, right? And this other component, the given number, right, that you have to achieve the exponentiation is going to be called the argument of the log. Okay, now, basically, to put it simple, the log is the exponent to which the base, this b, right, is raised to get the argument, to get this x, right? Is the exponent to which the base is raised to get some given number. Example here, what should be the log on base 5 of 25? Well, we gotta ask yourself, right? What should be the exponent I should place on top of this number 5 to get 25, right? And I see in the chat, students are already posting the answer, right? If I run the powers of 5, 5 to the first power 5, 5 to the second power 25. I got it, right? So very good, very good. Very good, Lucero, there. 2 should be the exponents, right, to which this base 5 must be raised in order to get 25, right? So because of that, we say this log is just 2. It's just 2. Great, excellent, excellent, excellent. Very good, guys, very good. Hughie, welcome. We're talking about logs, logarithmic functions. Okay, and we said that they are strongly related to exponential functions, right? They are the inverse functions of exponential functions. All right, so great. So now, but now it's tricky to get the log using these powers, right? Because imagine this number is big. You don't want to run this, 5, 6 times. It's a little bit tedious and tricky. Here, I'm going to give you a mnemonic device and a little strategy in order to get this result quickly. Turns out it is always possible to rewrite this logarithmic equation as an exponential equation. For example, here you can see out of our reasoning, right? Out of our reasoning that this guy 5 raised to a second power equal to 25 is completely equivalent to this guy, right? Log base 5 of 25 equal to. They are equivalent, right? But how can I go back and forth from here, right? Especially from the logarithmic form to this form quickly. There is this mnemonic device called snail it. Snail it, professor. Well, it's because you do this. 5 raised to 2 equal 25, the argument, right? This resembles somehow the shell of this animal, right, called the snail, right? The shell. So very often they say snail it. Mathematicians use this mnemonic device to go quickly from logarithmic form to exponential form. So log base 5 of 25 equal to, same as saying 5 raised to a second power, 5 raised to a second power equal to the argument 25, right? 25. We're gonna use this snail it mnemonic device a lot, so try to get used to it. So, or you can derive this from these exponential results too, right? But this is quicker, I guess. All right, great. So first thing I want you to master is how to go back and forth from this logarithmic form to this exponential form, okay? So we're gonna practice here on our worksheet. I want you just to rewrite these things. For example, number 1, could you rewrite this in a exponential form? Log base 4 of 64 equal 3. Anyone who figured this out, let us know, okay? Rewrite this in exponential form as an exponent, right? I see. Savannah, Lucero, very good. Excellent. Good job. Good job. I think you understood, right? It's nailed it. Look, if log base 4 of 64 is 3, 4 raised to the third power must be equal to the argument, 64. So 4 raised to the third power equals 64. Excellent, excellent. We're going to use this a lot when we solve this logarithmic equation. So very good, excellent. Can we try this one now? Number 2. This one. Log base 7 of 343. Notice the number is big. It will be hard to come up with a table, right? Not so efficient. So it's nailed it. We use the mnemonic way. Savannah. Very good, very good. You got it. Yeah, excellent, excellent, right? It's nailed it. 7 raised to the third power should be equal to the argument of the log 343. So 7 raised to the third power, 343, right? So therefore, we're talking about this guy. Excellent, excellent. This one, I leave it for you to do at home, okay? Okay, let's move on. Let's talk about now a special log, a special logarithmic function. The one having as a base the number 10. It's called the common log, or formally speaking, the common logarithmic function. The base is 10, okay? So this is defined to be log base 10 or simply log. Mathematicians have this agreement. If the base is 10, they don't write it. They will not write it. They will just write log. It will be understood that the base is 10. So first, let's learn how to evaluate common logs, right? In a calculator, for example, here, compute log, nothing written here means base 10, right? Of 100. Well, I go to my calculator, right? And you write log 100. We don't have to write the base, and this is just 2, right? And makes sense because 2 is the exponent that plays on top of the number 10. 2 to the second power is 100, right? It's 100. So in some cases, you will be able to get this doing some mental mathematics, but not always, not always. So that is the intention of this part, to show that in general, you may have to use the calculator. For example, here, log of 1/3. What should be log of 1/3? So you take your calculator, right? And type log, or you can pick it up also from functions. Here is here log, right? Doesn't matter. So then within parentheses, you're going to write 1/3, 1/3, close parentheses, and that should give you the result, right? Negative 0.477. There will be instructions for you to do the rounding. In this case, it's round to 3 decimal places will result, right? So rounding this to 3 decimal places, we will get 0.477 negative, right? 0.477 negative. So let me write this down. Negative 0.477. Excellent. Notice the result, the output value of these logs may be a negative number, okay? In fact, it could be any real number, this output value. However, the inside of the log must be always positive, must be always positive. So try to catch that. Look, what would happen if I attempt to get log of a negative number? Let's see together, right? Suppose I try to get log of the number -2. Undefined. And later I will explain to you why this is undefined, right? Why it does not make sense to take logs of negative numbers, but try to keep it in mind. Log of a negative number, undefined, okay? Undefined. All right. Now, some exercises for you to practice on these computations of common logs, right? We're going to use them a lot through the calculator. So I want to make sure that everybody's okay with this. So let's practice. Can you try this in your calculator? Let's try this guy, for example. It's pretty straightforward, right? It's 5. What should be log of 0.68? Professor, I don't see the base. Remember, guys, if you don't see the base is an invisible 10, right? Invisible 10. So I'm going to write it like using this continuous line, the 10, because it's understood this thing. Jing, let me double check. I think you're right. Very good, very good. Excellent work, right? Can also, right? Yeah, check, guys. Try it out. Can also great, right? Yeah, very good. We just go to our scientific calculator, right? I'm using our Desmos scientific calculator. And either I type log or I go to functions. It's going to be there too. Right here, log of 0.68. Close parentheses. Negative 0.167. Okay. Right? So, and that is a match with choice D, right? Once you round it to 4 decimal places, they are saying round to 4 decimal places, right? You're gonna go up to here, 4 decimal places. So up to here, since it's a 9, this becomes 5. Great. So this one approximately equal to negative 0.1675. The result, the output value could be negative, but the input value can never be a negative number, right? Try to keep it in mind. Now, can you try this one now? Yeah, I'm emphasizing on this because you're gonna take these logs a lot. So try to get that done. And then we will go over to number 7, we'll move on. What should be the common log of the number 1.892 rounded to 4 decimal places? Savannah, Jing, very good. Excellent, right? This time, if we use our scientific calculator or our Desmos calculator, log of 1.892 is simply equal to 0.2769, right? Rounded to 4 decimal places. Great, excellent. So this is it, right? Notice now positive, right? As I said, it could be a positive number, a negative number. The output value could be any real number, but the input always positive, okay? Okay, great. Now, to emphasize that fact, right, that the input has to be positive, what would be your answer if they ask you this question, this tricky question, right? Log of this number. What do you think should be, which choice you're gonna take there? Jing. Yeah, you made my day. Very good, excellent, right? Nothing to compute really, because we explained that if you attempt to take logs of negative numbers, the answer is undefined, right? Undefined means it does not exist as a real number, right? So you gotta go with this, does not exist. Excellent. Even if you forget, right? Let's say you forget that the log of a negative number doesn't make sense. Well, when you try to compute it, you will get a confirmation of that, right? Undefined, right? Very good. Great. Okay, guys. So now we're gonna use different bases, right? 10 is not the only base. So let's look at other bases. For that, I'm gonna give you some properties in general of logs in any base. Properties of logarithms. Mathematicians figure out that there are 3 fundamental properties for logs. The first one says log base b of the number 1 should be equal to what? Notice that this log base b of 1 is just the exponent to which I should raise this base b to get 1, right? Since we know that any positive number raised to 0 is 1, from here, I gotta say that this has to be 0, right? Always. No matter what the base is, if you take the log on base b of the number 1, the result has to be 0. Next, what if you take the log base b of itself, b? What should be this result? Anybody would guess what should be that? Aha. Jing Jing. Excellent, excellent, right? It is known that if we raise b to the exponent 1, we get b itself, right? So based on this, remember the exponent is the log, right? So 1, right? Great. Now, the third property deals with the fact that logarithmic functions are the inverse function of exponential functions, right? So let me give you sort of this information in advance. This is the graph of an exponential function in general, right? Remember, the graph of an inverse function is just the mirror image of this. We will see this in details later, but for now, let me just do this, right? Mirror image. So when you apply the horizontal line test to this mirror image of this exponential function, of course, this will pass the horizontal line test, right? This graph. So because of that, logarithmic functions are one-to-one. So therefore, if you have this situation, log base b of x equal to log base b of y, then x has to be equal to y. In other words, if the bases are the same, the arguments must be the same, because the logarithmic function is a one-to-one function. To equal bases, it corresponds to equal arguments, right? Great. So now we're gonna use this powerful property in order to solve some basic logarithmic functions, logarithmic equations. Sorry. So, for example, here I have log base 3 of x squared equal log base 3 of 49. Solve for x. So what do? Well, since logarithmic functions are one-to-one, if the bases are the same, the arguments must be the same, right? So here you have equal bases, 3, 3. So these two guys, the arguments, right? X squared and 49 must be the same, right? It's kind of, you drop the log part, right? And you just set these guys to be the same. So x squared must be equal to 49. Now, this is a quadratic equation. We know how to solve quadratic equations, right? If x squared is equal to 49, well, taking square roots in both sides leads to this, right? X equal plus minus square root of 49, but the square root of 49 is 7, so this leads to plus minus 7, right? Plus minus 7. So, two possible candidates for our answers, okay? X equals 7 and x equal minus 7. You said candidate, professor, why you say that? Well, turns out, guys, remember I warned you about logs in the following sense. You can never have a negative number inside a log, right? The argument can never be negative. So because of that, whenever you get the solutions, when you're dealing with logarithmic equations, you are supposed to check your solutions, okay? To check your solutions. Sometimes both candidates will check, so you will take them both, but sometimes just one of them will check. Sometimes even both may not check, right? So you may say no solution. All right, so let's check. Let's start with x equals 7. To check, you go back to the original equation, to this original equation that you were given to solve, and there you are going to substitute the candidate for a solution for x, right? And then you will ask yourself if this statement is indeed true, right? Let's see. All right, if you work this out, log base 3, 7 squared is 49, equal log base 3 of 49, perfect match, right? So it means that it checks. So this one, good, right? Okay. Let's check x equal -7 now. X equal -7. Check, right? Again, you just place inside the equation, instead of x, this number -7, right? And you check if this statement is actually true. -7 squared, -1 squared is 1, 7 squared 49, right? 49. So you end up again with this. Well, perfect match, which means that this guy also checks, right? It's okay. This guy, okay. So both solutions are good, right? This and this. So therefore, solution set will be equal to, within braces, separated by commas, you write these two guys. That's it, right? So both check. So solution set is this. We can write this as a conclusion, right? Conclusion. So the moral of the story is, when you're dealing with logarithmic equations, always check, guys, okay? Always check. Here is another one, before I give you some exercises to work on. Suppose they ask you to solve this. Log of 10x minus 2 equal log 3x plus 19. Professor, there is no base. If there is no base, it just means that the base is 10, right? The base is 10, so we can write it as 10. Now, what is important here is that the bases of these two logs are the same, right? The bases of the two logs are the same. So we have a property that says that if the bases of the logs are the same, then the arguments of the logs have to be the same as well, right? So we drop the logarithmic part and we set this argument to be equal to this argument, right? 19. And now we have a linear equation, so shouldn't be difficult to solve, right? First, I'm going to transpose this term to the left side. For that, I am subtracting 3x in both sides. I get this. And then adding 2 to both sides, I get that 7x equal 21. Dividing by 7, sorry, both sides, I get my solution, right? 21 over 7, x equal 3. X equal 3. Okay, now this is a candidate for a solution. You must check in order to make sure that this is a good solution. X equal 3, check. In the original equation, you substitute here 3. Okay, here also 3. So what we're gonna get out of doing that? Well, you're gonna get the following: log 10 times 3 minus 2 equal log base 10, right? We don't have to write the base 10 agreement of 3 times 3 plus 19, right? 3 times 3 plus 19. All right. 10 times 3 is 30 minus 2. 30 minus 2, 28, right? On the other side, you have 3 times 3, 9. 9 plus 19, 28. Perfect match, right? Perfect match. So it means that this is correct. So the solution is okay. Great. So solution set is going to be equal to this. Within braces, just the number 3 alone, right? That's it. Excellent. Here is another one that deals with quadratic arguments. I want to do that, but first I want you to practice here, okay? Let's go back to the worksheet and let's see if you can solve some basic equations. Okay, so, and before that, probably just to check, we should try this one. Based on the properties, try to do this. What should be log base 16 of the number 1 based on the first property, I think is that right? Jing, excellent, right? Very good, very good. Yeah, remember the log is just the exponent you are supposed to place on top of the number 16 to get the number 1, right? It is known that 16 raised to 0 is 1. So this guy, it was goes here, right? It's a property, right? It's a property that is 0. Logging any base of the number 1, 0. Very good, excellent, excellent. Great. Now, let's solve a linear equation. For example, let's try this one. Can you try it? Hint, since logs are one-to-one function, to equal bases, it corresponds equal arguments, right? So basically set the arguments to be equal and solve for x, right? And after that, just to play safe, simplify your answer, right? Your answer. Not simplify, check your answer, check. Yeah, check and make sure that it's not giving you any trouble. Check that indeed it gives you a true statement when you replace x for the candidate for the solution, right? Yeah, great. So go ahead now, 13. I see readily students posting answers. Yeah, great. Very good, Jing. Very good, very good, very good. So yeah, give it a shot, work it out. And these are basic logarithmic equations. Later, we will complicate them more, right? We'll go over more challenging equations. All right. Yeah, if you drop the logarithmic part, right, this is the same. This logarithmic part is the same as this. The bases are the same. So you drop it, you set equal the arguments, you end up with a linear equation that can easily solve by subtracting 2x in both sides, right? And then adding 7 to both sides. Different ways to solve these equations, right? Just follow any method you're comfortable with. You will end up here, and x will be 12 over 3, x equal 4, right? Candidate for my solution. But remember, we're dealing with a logarithmic equation. We're gonna check in the original equation, which is this log base 5 of 5 times 4 minus 7. Is this really equal to this, right? Or I'm gonna give you this hint. At least we have to check that these arguments are not negative, right? If you determine that these arguments are not negative, that's good enough. It will check, right? I will show you. 5 times 4, 20, minus 7, 20 minus 7, 13. Log base 5 of 13. Positive, right? Positive. So it means that we are not in trouble. It's good. This one, 2 times 4, 8 plus 3, 13, also positive. So you can see, right? It will check. As soon as you determine that these guys are positive, you can make sure that, you can be sure, better said, that this will check. This will check. So check, this is good. So then you say solution set will be just 4, right? Within braces. Excellent, excellent. Here there is a logarithmic function that deals with a quadratic form. So let me show you how to deal with that. So let's go back to a lecture. The principle should be the same, but now you have to be really careful when you do the checking. I will show you why. Okay, so suppose they ask you to solve now this logarithmic equation. Log base 4 of x squared minus 6 equal log base 4 of x. Remember, quickly, you notice that the bases for the two logs, they are the same, equal to 4, right? So basically, you drop this part, the logarithmic part with a base, right? They are the same, right? Drop it and set equal the arguments, right? The arguments. So x squared minus 6 equal x. Now, to solve this quadratic equation, remember the technique is bring everything to one side of the equation and choosing that side to be the left side, right? And let the other side be equal to 0, right? 0. You may say, why we are doing that for quadratic equations, Professor? Well, it's because this allows us to do factorization. If you factor this guy, then you can get quickly the solutions. Two numbers whose multiplication is 6, whose sum -1, invisible one here. After some trial and error, you will find out that those numbers are 2 and 3. You want the sum to be -1, so the dominant in sign should be this, right? It's plus, right? This is what we get. Next, we set each of these factors equal to 0. And from there, you should get your candidates for your solution, right? X equal -2 plus 3 gives you x equal 3. Two candidates, right? Professor, why you call them candidates? Well, because you have to check them before you claim that they are actual solutions. Check. I'm going to start with this guy, x equal -2. Look, this guy, x equal -2, when substituted into the original equation, it is always the original equation, the one that you must use for your checks. Log base 4 of -2 squared minus 6. Is this really equal to this? Log base 4 of x? No question mark here, right? Look, -2 squared is -1 squared is 1, 2 squared 4, so it's 4. 4 minus 6 is -2. Aha, look, trouble here, right? Trouble, look. Remember what happens when you try to take the log of a negative number? That is just nonsense, right? Here again, look, trouble. X, -2, right? This is undefined. So this is not checking because it's giving me something undefined here, something undefined here. Even though the forms are the same, this does not make sense, okay? So I'm gonna write here, does not make sense because this is undefined, okay? It does not make sense. Because of that, guys, you are supposed to ignore the solution. So when you see that it doesn't check, it's not okay, not a solution. Okay. Okay, great. So this guy, not good, right? Not okay. You just ignore it. Let's check x equal 3 now. X equal 3. So we take our original equation, which was this, right? And there we substitute 3 and see if indeed this guy is equal to this guy, right? 3 is 3. Question mark here. 3 squared is 3 times 3, 9. 9 minus 6 is 3, right? 3. So this is log base 4 of 3. This is also log base 4 of 3, right? Positive here, no trouble. This checks, perfect match, right? So this means that this guy is okay. Okay, right? Great. So this guy good, right? So conclusion should be solution set is just this. Within braces, you put the ones that check, right? Just 3, right? Not -2, right? Just this guy, right? Be careful there, guys. Okay? Just number 3, not -2. Okay? All right. So now that I show you how to deal with this quadratic form, right? Just very careful with the checking there. Try this guy. And if you have questions, guys, always let me know, okay? If it's something not clear, please let me know. Let's try. I saw a quadratic form here. Yeah, I think we can try number 16. All right, so let's try this out. Yeah, great. This is good. 14, right? 14. I'm gonna write it bigger here. Log base 6 of x squared equal log base 6 of 3x plus 28. Right, that's the equation. Try to solve it, guys. Remember, the hint is, since the bases are the same, right? Since these parts are the same, drop that, or drop that, just set equal the arguments, right? The arguments. So just write it out so you can work on that. And solve this quadratic equation. Once you get your solutions, check them, right? Check them. Hint, try to move or transpose these two terms to the left side, leave 0 here so you can factor, right? You can factor, you can use ultimately the quadratic formula if needed, right? So go ahead. And always check your solution. Sometimes both solutions are good, sometimes just one is good. Depends. Depends on the equation, right? Yeah, it's tricky. So give it a shot, give it a shot. Huh? Good, Jinjing. Great. Very good, very good. Yeah, excellent job. Tricky, right? Okay, so let's do it together so we can go over more examples. If I transpose 3x to the left side, that is accomplished by subtracting 3x in both sides. You're gonna get here x squared minus 3x equal 28, and subtracting 28 in both sides of the equation, you end up with this: x squared minus 3x minus 28 equal 0, right? 0. Now I'm gonna try to factor. In general, if this is not factorable, you may have to use the quadratic formula, but I think it's factorable, because if you look for two numbers whose multiplication is 28, whose sum is -3, those two numbers, after some trial and error, must be 7 and 4, right? You want the sum to be -3, so 7 should be negative, 4 should be positive. Great. Now, from there, I can say that the candidates for the solutions should be x equal -4, right? One candidate, and x equals 7, another candidate, right? After adding 7 to both sides, x equals 7, the other candidate. So now let's check, right? Let's check if they are good solutions. So check. To check, if you substitute x equals -4 into the original equation, into this one, right? Is this really true? Let's check. Log base 6 of 3 times -4 plus 28. -4 squared is 16, right? So you got log base 6 of 16. Positive number, right? So good. Here, this is -12. -12 plus 28. -12 plus 28. 16 also, right? 16. Positive, positive, so good. This is checking, so this is good, a good solution. Let's check the other one. X equals 7, right? X equals 7. And again, guys, if you want to shorten the checks, just make sure that the arguments are positive. If the arguments are positive, mathematicians have determined that it will check, it will check. So you can sort of shorten this process by just making sure this is positive, which is the case, right? Look, 7 squared positive, 3 times 7, 21 plus 28 positive, right? That should be enough to claim that this is good. A log base 6 of 49 equal log base 6, 21 plus 28, 49 as well, right? So we check. So here, again, it's enough to show that this is positive and this is positive to verify this candidate as a good solution. So they're both good. So conclusion then, the solution set should be -4 together with 7, right? So you can see, guys, it depends on the example that I did, only one check, but in this particular example, both check, right? So be careful there. So 7 and -4 in any order, that's it. Very good, very good. Can you try now this one? Yeah, I will write this bigger so you can all see. Solve this equation. Log base 9 of x squared equal log base 9 of 6x plus 7, right? It's very close to the one that we just did with different numbers. So give it a shot. Try and figure out the solutions. Sometimes the students ask me, Professor, what is this symbol here? This is a symbol. It's called phi, means no solution. So in case you check your solutions and none of them checks, you gotta go for this. It's not 0. It means just no solution. It's a 0 with a slash. Right? Mathematicians use this symbol to express that there is no solution. For number 15, let's double check. Jing, great, excellent. Very good, very good. Good job there. Very good, very good. Yeah, remember, guys, when you have two logs and they have the same base, you just drop this part, right? And you set the arguments to be equal to each other. And you may say, Professor, what happened when the base is different? I will show you more strategies when the base is different, right? Tomorrow, for example, we're going to see very, very challenging logarithmic equations, but we have to make sure that the basic stuff is well done first. All right, so setting this equal, remember, when you transpose this to the other side, this to the other side, you're gonna get this, right? X squared minus 6x minus 7 equal 0, right? Subtracting 6x in both sides, subtracting 7 in both sides. Great. Just like we did before. Now, let's see if we can factor, right? X. I need two numbers whose multiplication is -7, whose sum is -6. After some trial and error, you will figure out that those numbers are 7 and 1. You want the sum to be -6. This negative, this positive. Now, setting each factor containing the variable equal to 0, we're going to get these two candidates for the solutions. X equal -1 from here, right? and x equals 7 from here. These are candidates, right? In order to determine if they are good solutions, you have to check. So let's start by checking x equals -1. On the original equation here, right? You substitute x for -1. Okay. Here log base 9 of 6 times -1 plus 7, right? And I gave you this shortcut, right? Just make sure that the arguments are positive. If the arguments are positive, this will check. So let's follow the shortcut. This is 1 positive. This is log base 9, 6 times -1, -6 plus 7, 1 positive, right? So this will check, as you can see, right? So this is good. Now, the second one is this one, x equal 7, right? Check. Again, right, you write log base 9 of 7 squared. Is this equal to log base 9 of 6 times 7 plus 7? Notice this is positive. This is positive. They're both 49, right? So if you determine that they're both positive, it's enough. It will check, right? 49. Good. So this means that this one is also okay. Conclusion, solution set -1, 7, right? -1, 7, which is this one. Excellent, excellent. Okay, guys. Now let's talk about how to graph these logarithmic functions. Okay, let's talk about that. How to graph the logarithmic functions. So let me explain that to you here, and then we will take a break. So let's go over this. Graphs of logarithmic functions. To sketch the graph of y equal log base b of x, use the fact that the graphs of inverse functions are reflections of each other about the line y equal x, right? Y equal x. Remember, the graph of a given function and the graph of its inverse function, they are reflections of each other about this diagonal line y equal x, right? It's like you place a mirror here, and over here you should see the mirror image of this, right? Yeah, so, but to be practical, a quick way to see where this point is going to appear on the other side of the mirror, I gave you this trick, right? Switch the coordinates. Here, for the exponential function y equal to the x, for example, the y-intercept is 0,1, right, as we explained yesterday. So the corresponding point here on the other side of the mirror, in the reflection, will be 1,0, right? Similarly, this guy with these two coordinates, you switch the coordinates, you get this, right? Or simply draw a perpendicular to this y equal x and go the same distance, right? That's another way to get it. So you get a bunch of points. What is important is that when you connect all those points, what you're gonna get is this curve, right? Like this. This will be the equation of y equal log base 2 of x, right? Log base 2 of x. Notice for the exponential function y equal to the x, yesterday we explained that this is the, let's use a different color. This is the horizontal asymptote, right? Horizontal asymptote y equals 0, right? For y equal log base 2 of x, this horizontal asymptote, given the reflection about this line y equal x, will become this vertical asymptote, right? So this one, let's use a different color here, will be a vertical asymptote here, vertical asymptote. So let's use this orange. This, which was the horizontal asymptote in the original graph, in the graph of log base 2 of x, will be a vertical asymptote, and it's going to be x equals 0, right? Here y equals 0, horizontal asymptote, here vertical asymptote, x equals 0 for this function, right? Y equal log base 2 of x. Okay. Now, in the homework, there's a question that you're going to encounter that will ask you to express the relationship between the graph of the exponential function and the graph of the logarithmic function. One answer you can say is that they are reflections of each other about the diagonal line y equal x, right? Yeah, try to keep that in mind. Okay, guys, so here an example. It says graph f of x equal log base 3 of x minus 2 and find the domain and range of f of x. Okay, this example is going to help you with your homework, so let's try to understand it. All right, when you are asked to graph a transformation of this basic form, log base some number, in this case was 2, but it could be 3, 4, right? Any positive number. Do the following. Start with something that you know. We know the graph of this basic function, right? Y equal log base, in this case, 3 of x. So what's that? Well, the x-intercept is always here at 1, 0, right? And the graph shows this asymptote, right? This vertical asymptote. The graph gets closer and closer to that vertical asymptote but never touches it. So just like this, right? Yeah, great. This is the graph of y equal log base 3 of x, this part, right? This part. So start with something that you know. That's that. Now, but you want the graph of this guy, right? But notice that this -2 is just telling us that we have to shift 2 units to the right horizontally, this graph or this curve. When you do the shift, as I explained yesterday, shift important features of the graph. For example, shift this x-intercept, right? Which is original at 1, 0. But if you shift this 2 units to the right, where will it appear? Well, this is here 1 unit away from the origin. Here 1, 2, it will appear here, right? You see it, guys? It will appear here. So the new x-intercept is going to be located at 3, 0 now, right? Now the asymptote here, it's at x equals 0. But since you're shifting 2 units to the right, the asymptote will appear now here, right? Will appear now here. Here. The vertical asymptote. So shift the main features, right? The x-intercept and the vertical asymptote. Now, finally, the new graph will be this, right? Then you draw the curve there, right? Asymptotic to this guy. And it's like this increasing curve from left to right. Now, this will be the graph of y equal log base 3 of x minus 2, right? Now, from there, it will be easier to figure out the domain and the range. What should be the domain here? Domain. Anybody could tell me based on this graph, right? Notice this is the number 2 there, right? 2. And here is where infinity is, right? Anybody could guess the domain of this new graph by looking at it? I see something on the chat. This chat. Guys, you made my day. Jing, Savannah, right? Very good, excellent, right? And this is something that you have to recall for your homework. It's a question very similar to it, right? Do the transformation, but with the asymptotes, with the x-intercept, that will help you with the domain. So the domain clearly has to be starting at 2, not touching 2, right? Because the graphs, notice the curve gets closer and closer to 2, never touches 2 horizontally, right? So, and up to infinity, right? You never touch infinity, so this. Now, what about the range? Can you guys figure out the range? What should be the range? Notice that this graph increases to the right forever, right? So, and also decreases down forever. So hint, right? Here, infinity. Here on the bottom, negative infinity. So what should be the range? Savannah, you made my day. Minus infinity, excellent, excellent. Minus infinity from here, the lowest point for the output values, right? Up to infinity, right? Infinity, yeah. So try to remember these guys for your homework. It's a similar question. All right, but now let's try to practice, right, in our worksheets. Now, what kind of questions relate to this? Well, I will show you now. A nice question here. We can do. Here. What about this? Could you figure out what is the graph? Let me show you. Yeah, this is the graph. This, right? F of x equal log base 2 of x plus 2. What is the graph? Which one of this? This, or this? Figure this out, please, and let us know in the chat. Let's see. Lucero. Well, good, great. Jing also great. Excellent, guys. Excellent. I'm glad that you're tuned, you're following all this. Yeah, great, right? Remember, start with something that you know, right? Something that you know. And something that we know is that the graph of this guy, f of x, natural log of, not natural, log base 2 of x, right? Base 2 of x is just this curve, right? This curve, and goes through one. It has this vertical asymptote there, right? But now I want you to shift this 2 units to the left now, right? 2 units to the left. Why 2 units to the left, Professor? Because this is how this horizontal shift work, right? It's counterintuitive, right? 2 units to the left. And if you follow where the x-intercept is going to go, where the vertical asymptote is going to go, it's going to be here, right? There you go. This is the vertical asymptote, and this is going to be the x-intercept. It was 1 unit to the right here, but since you're moving 2 to the left, it will appear here, right? Excellent. So this is it. This point is going to be negative 1,0, right? 1, 2, yeah, to the left. And the asymptote will be there. Excellent, guys, excellent. Very good. Next question, this one you can do it at home. The other, let's talk about natural logs now, natural log, ln. Remember, yesterday we studied the natural exponential function, the exponential function having the base e Euler number, right? So it's called the natural exponential function. So mathematicians notice that this natural exponential function, whose graph is this, yesterday we explained, right, is a one-to-one function. So therefore it has an inverse function, right? And the inverse function when graph will be the reflection of this exponential function about the line y equal x, about this line, this diagonal line, right? It will be this. They call this function the natural logarithmic function. It's the inverse function of the function f of x equal e to the x, right? So it's this, f of x equal natural log. Natural log is expressed as ln of x. Now, you may say, Professor, the base shouldn't be e. Agreement when the base is e. mathematicians don't write the base e, they drop it. They just write, instead of log base e of x, ln of x, natural log of x, right? This means log base e of x. That's it. And basically from there, you can understand this natural log function as the inverse function of g of x equal to dx, right? Let's start by showing how to do some computations with this natural log of x function. For example, if they ask you to compute natural log of the number 5, they are basically asking you to do log base e of 5, right? But mathematicians call it ln to that. So, and since this is an important function, moreover, when you go to the scientific calculator, there is going to be a function reserved for natural log. You will see right here, ln. You see, ln. ln of 5, natural log of 5 is equal to 1.6094. They will say rounded to some number of decimal. They say rounded to 3 decimal places here. So it will be 1.609, right? 1.609. 1.609. This is the natural log of the number 5. Natural log now of 0.3. So you go back to the calculator and then you either type ln from the keyboard or you look for your natural log function within the set of functions that are given in your scientific calculator. Every scientific calculator has the function ln, natural log here in this case, right? Or you just type ln. 0.3 now, 0.3 is the argument. Output negatives, negative 1.203 followed by a 9, so negative 1.204, right? Rounding to the nearest 1,000. So negative 0.1204. Not this is negative 1 point, sorry. Very good, guys. So this is what the computation gave us, right? 1.204, round to the nearest 1,000. All right, great. Now, sometimes they will ask you to solve this type of very basic equations. How you solve it? Say solve natural log of x equals 7, show answer in exact form. All right. Here, we're going to use our mnemonic device that are advertised called Snail It, right? I have a logarithmic form. I want to translate this into an exponential form. The base is e, not written, but understood that it's e. So all I do is this, I snail it, right? So if you snail it, look, e raised to 7 must be equal to x, right? So you do e raised to 7 equal to x. But then that's the answer, right? You were supposed to solve for x, e to the 7. When your answer is written in this form, this is called exact form, exact form, exact form. And often they use this exact form, right? But now, if you want to compute it, right, as a decimal, not a problem, because you go to your calculator, you go to functions, go to e to the x, just put 7 on the top, then you get 1096.63, right? 1096.63. 1096.63 will be this in decimal form. So this is what mathematicians call decimal form. But for this, you need instructions to do a rounding, right? Decimal form. So pay attention to the instructions on your homework. If they say exact form, you show this. If they say approximated form rounded to 2 decimal places, let's say you show this, right? All right. So now transformations can be applied also to logarithmic functions when the base is c to natural logs. Here is an example. Suppose they ask you to graph this guy, natural log of x plus 1. I explained, right? Start with something that you know. For example, this. And then translate this 1 unit to the left, right? 1 unit to the left. So this is the vertical asymptote. This is where the curve meets the x-axis at 1, 0, right? So this guy will appear here right here at the origin, right? Because you are shifting 1 unit to the left, 1 unit to the left. All right, so it will appear here, and the vertical asymptote will appear 1 unit to the left from the origin, right? Here will be the vertical asymptote. So right there, you draw this, right? And that's it. This will be y equal natural log of x plus 1. Okay. Here's another example, minus natural log of x minus 2 plus 1. This negative in front of natural log means that you have to apply a reflection. This means 2 units to the right, and this 1 unit up, right? 1 unit up. So start with something that you know, remember this guy, 1,0 here. This point, when you reflect it, will stay there. But when you move it 2 units to the right, will appear here, 1, 2, here, right? So somewhere there, 1 unit away. This vertical asymptote will appear 2 units to the left now of the origin, right? Say there. Right there, you're supposed to get this done, right? But however, notice you are dealing with the reflection of this, right? The reflection about the x-axis. So finally, this will be like this, right? You follow, guys? Yeah, very good, very good. So finally, this will be like this. And on top of that, you are shifting everything up 1 unit, right? So after you do this reflection, you're going to raise it up 1 unit. So finally, we'll end up there. Okay. So you just follow the rules of transformations that we follow before, right? And then you should be fine. Yeah, great, great, great. So up, right? Okay, great, great, great. This is nicely. Okay, great. So this is it, right? Excellent. I have a question here. To the right. To the right. Yeah, excellent. Yeah, this is negative, so we should move to the right, right, instead of to the left. Yeah, great, 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 great comment. So let's just redo this because I moved to the left for some reason. Let's do this quickly. Yeah, maybe we should write here, right? The 3 steps, the 3 steps. So now I guess what you reflection, 2 units to the right. And because of this, 1 unit up, right? 1 unit up. Yeah, I was still thinking on the previous. So in the end, you should get something like this, right? Yeah. You should get 2 units to the right. 1, 2, 3 is here where your x-intercept will appear. Then 1 unit up will end up here, right? And the asymptote will stay there, right? So, and since you are dealing with the reflection of this, should be this, right? Reflection. Very good. Okay, guys. Yeah, this is for you to complete at home. Very good. Now let's go back to some word problems. No word problem. Yeah, there's a word problem at the end that I will go over to show you how these logarithmic functions, they lead to modeling somehow. But now I want you to try this with ln, and then we will quickly move away from this. Try this. You will use this in your homework. Try to graph ln of x minus 2. And show how is this gotten with respect to f of x equal ln of x, right? Remember the hint, start always with something that you know, which is just this guy, and go from there, right? Go from there. Start with this, right? And this is telling you that you should shift 2 units to the right. Yeah. So what do you think should be the answer there? Let's see. The students readily posting answers. Savannah, great. Very good, very good. Lucero also, very good, very good. Yeah. Excellent, right? 2 units to the right means that this originally has coordinates 1, 0, right? If you move these 2 units to the right, it will be 2, 3. It will appear at 3, right? So here, perfectly right. You here 3, right? 1, 2, 3. This one, 3, 0, right? And the vertical asymptote, which is here at x equals 0, once you translate it to the right, 2 units will appear at x equal 2 now, right? Yeah. The vertical asymptote at x equals 2, right? Here was at x equals 0, vertical asymptote, right? Yeah, great. And that's it. Excellent. Move right 2 units. Great, guys. So I hope you will be okay with the graphic. Now, let me show you this example that will illustrate how we deal with these equations whenever we don't have two bases that are equal to each other. We cannot drop the logarithmic part, right? I will explain this to you. I will ask you to do 29, okay? So suppose they ask you to solve this logarithmic equation. Log base 6 of x squared minus 5x equal 1. I don't have a log here. I have only a log on the left side. Whenever that happens, use the mnemonic device, snail it. Snail it. Look, snail it. If log base 6 of x squared minus 5x is equal to 1, it means that 6 raised to 1 must be equal to this guy, right? You follow, guys? So 6 raised to 1 has to be equal to x squared minus 5x, right? From there, you can solve this quadratic equation, right? Easily. Let me move the number 6 to the right so I can leave 0 here. X squared minus 5x minus 6, right? So now solve that quadratic equation. Hint, use factorization, right? If possible. Worst case scenario, you can use quadratic formula. But I can see that here it is possible to factor, right? I need two numbers whose multiplication is -6, whose sum is -5. After some trial and error, those numbers are 6 and 1. This guy negative, this guy positive. From here, we've done this before, I get x equal -1, the first candidate for my solutions. So another candidate here, x equals 6, right? Two candidates. But turns out, since we are dealing with logarithmic equations, we must check our solutions, right? Check. So start with x equal -1. Warning, guys, the fact that this is -1 does not mean immediately that you have to drop it. Sometimes negative values check. You will see. You will see. What is important is that the inside of the log must be positive, right? Must be positive. This is really the key for this candidate to check as a solution, right? So is this equal to 1, right? I'm using the original equation. Always you check using the original equation, right? This in this case. All right, is that true? Well, if you work it out, -1 squared is 1, -5 times -1 is 5 positive, 5 plus 1, 6, right? So notice, this is saying that this should be equal to this, right? But we had a property, right? We said log base b of itself is equal to 1 always, right? So checks, right? So this is 1, so 1 equal 1, perfect match. So this is a good solution. So this is good. Okay. Let's check the second one. Check x equal 6. Log base 6 of 6 squared minus 5 times 6. Is that equal to 1? Let's see. 6 squared is 36. 5 times 6 is 30. 30 subtracted from 36 is 6, right? So this is saying, is this true? Because of our property 1, we know that this is 1, right? So perfect match again. So true. So this one, okay, right? Okay, we checked. So the two solutions should be -1 and 6, right? So -1 and 6. So conclusion, solution set -1 and 6. So you go here and look for the one that is showing both. Okay, can you try now, guys, the other one, this number 29? I will leave this for you to look at the rest as a reference, right? It says log base 9 of x squared minus 8x, right? Equal 1. Try it out. I see some activity on the chat. Let me double check. Work it out, guys. Number 29. Yeah, the hint is nail it, right? Hint here is nail it, right? To go from logarithmic form to exponential form, right? Yeah, great. Lucero. Let me double check. Lucero, great, excellent. Very good. Very good, very good. Yeah, very good, guys. It's nail it, right? It's nail it. And it's very similar to the one that we just did before, right? It's nailing it. 9 raised to 1 should be equal to x squared minus 8x. Bring 9 to the right side so that you can have 0 on the other side, x squared minus 8x minus 9. Factor. If you factor, you need two numbers whose multiplication is 9, whose sum is -8. After some trial and error, those numbers are 9 and 1, right? Minus here plus 1 here equals 0. From there, the candidates are 9 and -1, right? Yeah, so when you check as I did here, turns out this is a good one and this is also a good one. They are both good. So solution set 9 and -1. 9 and -1, which is here, right? Yes. Excellent. Yeah. Now, this is another form. Let me show you, and then I will ask you to do this other form, right? Let's say they give you this form here, log base 4 of x squared minus 10x plus 34, and they say this is equal to 1. Again, you don't see log in both sides, so a good idea, a good strategy is to snail it, right? Snail it. This means that 4 raised to 1 must be equal to this argument, right? So 4 raised to 1 equal x squared minus 10x plus 34. Transpose this to the left side by subtracting 4 in both sides, right? So 0 equal x squared minus 10x plus 30, right? Plus 30. Factor, right? I need two numbers whose multiplication is 30, whose sum is -10. After some trial and error, this number should be 3. And then we'll do the job. 15 times 2, 6 times 5. You see? Yeah, this guy is 11, sorry. It's very small, I didn't see it. 12. Yeah, this guy is just 11. All right, so we look for two numbers whose multiplication is 30, whose sum is -11. After some trial and error, 6 and 5 negative 6, negative 5, right? So the sum negative 11. Very good. Equal to 0, which leads to these two solutions, x equals 6 and x equals 5. These are going to be the candidates, right? But remember, we have to check them. We have to check them to see if in reality those guys are going to end up being the solution. So let's do a check here. Let's use a red color so we don't mix this up. That x equals 6, check. If you check x equals 6, remember it is enough to show that the inside of the log is positive, right? If you get to determine that, then you are done with the check, right? Look, 6 squared, 36. Minus 66 is going to be minus 30 plus 34, 4, right? 4, positive. So this is telling me that then this is going to check. So you may stop right there, right? This is going to check. Look, log base 4 of 4 is of course 1, so checks. This one checked. What about x equals 5? X equals 5, let's check. Then you're going to see if log base 4 of 5 squared minus 11 times 5 plus 34, if this is indeed equal to 1. 5 squared is 25. 25 minus 11 times 5, 55 is negative 30, right? But negative 30 plus 34 is positive 4. So positive again, right? 4, so it should check. And indeed it does, because log base 4 of 4 is actually 1, right? So great. So this one checks too. So finally, conclusion, solution set should be 6 and 5, right? In any order within braces. So 6 and 5. So you got here this guy, right? Very good, very good. So now, can you try this one, number 31? This one, please try this out. Similar, very similar. I'm going to leave this for you to have as a reference. Solve this equation, right? Log base 3 of x squared minus 7x plus 15 equal 1. Go ahead, please. Kang, very good, Kang. Very good, you got it, very good, excellent, excellent. Remember, guys, always check. But again, it's enough that the inside of the logs are positive. So if you get to determine that somehow, then it will check. The trouble is when those numbers inside the logs called the arguments are negative, right? This is very, very trouble. Go ahead. Hint, since you have log only in one side of the equation, it is a good strategy here to snail it, right? Snail it as I did before. So snail it. Go from logarithmic form to exponential form, solve the quadratic equation, test the solutions that you get, and keep the ones that are good. All right, let's do it together. Okay. Yeah, very, very good, Ken. Very good. If you snail it, you're gonna get what? 3 raised to 1. 3 raised to 1 should be equal to x squared minus 7x plus 15, right? 3 raised to 1 is just 3. So subtracting 3 in both sides of the equation, we're gonna get 0 equal x squared minus 7x plus 12, right? Plus 12. Let's try factorization. Let's look for two numbers whose multiplication is 12, whose sum is negative 7. After some trial and error, you will figure out that those two numbers are -3 and -4, okay? From here, x minus 3 equals 0, leading to x equal 3 as the first candidate for our solutions. And by setting x minus 4 equals 0, x equal 4, second candidate. Now, you got to check these two guys, right? Check. If you check x equal 3, in the original equation, right, in this equation, you got to verify that log base 3 of 3 squared minus 7 times 3 plus 15 is indeed equal to 1. 3 squared 9. 9 minus 21 is minus 12. Minus 12 plus 15, 3, right? So positive number. So that's enough. It will check. And indeed it does, right? This is 1. Good. So which tells us that this is a good solution. X equal 3, a good solution. And the other one, log base 3 of. The other solution is x equal 4. Equal 4. Log base 3 of 4 squared minus 7 times 4 plus 15 is this equal to 1. 4 squared 16 minus 28 minus 28 minus 15 is 16, right? Minus 28 plus 15 is just 3, right? 3. So 3. So this one also checks, right? Log base 3 equal 1 checks. So both check, right? Both check. So therefore we have to take both, right? Both 3 and 4. So 3 and 4, the one that is saying that is this. Great, excellent. Now, before I show you this, the number 32, let me see if you can solve this one. That is a little bit tricky, but simple. Can you try this? And I want to emphasize this idea of the exact form. Solve and show your answer in exact form. In exact form, right? So try to solve this. Natural log of x equal to. Can you do that? Mm-hmm. Hint is nail it, right? It's nail it after noticing that the base here that you don't see is by agreement E, the Euler's number, right? Euler's number. Jing, very good. Savannah, also very good. Excellent, guys. Excellent, right? Whenever you see just log in one side of the equation, on the other side you see a number, a very good hint is to use this mnemonic device called snail it, right? Snail it. So log base c of x equal 2 or natural log of x equal 2 means that e raised to 2 must be equal to the argument x, right? So e raised to the second power is equal to x. But this is the value of my solution, right? So x equal e to the second power. Now, this is an exact form. Now, if you check this here, of course, this e raised to the second power is a positive number, right? And natural log of e to the second power is precisely 2 because the log, remember, is the exponent. So it checks, right? Maybe I can write so nobody gets confused. Check. Natural log of e to the second power is this equal to 2. Property, right? Log base b of b is just the same, right? So this is the log, precisely the exponent, right? So this we checks. Great. So this is it, right? In exact form, right? They want it in exact form. So we're talking about this guy, right? Mm-hmm. Yeah, excellent, excellent, guys. Yeah, very good. Now, let's go over this last problem that I want to explain. This is going to serve you for your special assignment 2. As I explained, it is possible to do modeling with these logarithmic functions. For example, scientists, as you should know, they utilize these logarithmic functions to model earthquake. The intensity of an earthquake, right, is well known. But in science, there are a whole variety of modeling with this logarithmic function. This is just another example. I will explain it to you. It says, and I will ask you to solve it if you can solve it, okay, first, and then I will go over it. It says the function f of x equal 1 plus 1.5 times natural log of x plus 1 models the average number of free throws a basketball player can make consecutively during practice as a function of time, where x is the number of consecutive days the basketball player has practiced for 2 hours. After how many days of practice can the basketball player make an average of 9 consecutive free throws? Okay. All right. So here, basically, they are giving us a logarithmic equation that is modeling this particular situation, right? So they are asking you, given this fixed output value, which is 9, right? 9 consecutive free throws, what should be the input value such that when you plug it into this function, the output should be 9, right? Consecutive free throws. So let's start by writing out the equation that models the situation. Do it nicely here. And I will ask you to attempt to solve it. If you can do it, good. If not, we will do it together. It's a little bit tricky. Yeah, but doable. So this is the function, right, that models this particular situation. Now they're saying, right, what should be the input value x such that f of x is equal to 9, right? Yeah, so let f of x then be equal to 9, right? If f of x is equal to 9, right, then you have this equation, 9 equal 1 plus 1.5 times natural log of x plus 1, right? Now, solve for x. Can you solve this for x and figure out the answer? Hint, try to move this one to the left side, right? Transpose this to the left side. Try to isolate this part of the equation, okay? So first hint, subtract 1 in both sides, right? Start there and then try to see if you can solve it for x, okay? And try to remember this for your special assignment 2, which is gonna come together with after you take your exam 2. Aha, see. Students are posting answers. Lucero, excellent, excellent job. Very good, very good. Yeah. Let's just wait a little bit for other students to try, right? Very good, excellent, excellent. Good work there. More students posting. It's not that difficult, really. It's just a little bit tedious. Jin. Great, great. Excellent, excellent. Yeah, I'm glad, guys, that you are picking this up. Very good, excellent, excellent. Yeah, it's not that, it's not impossible. It's just doable. You gotta do it slowly, little by little, right? Isolate natural log of x plus 1, and then from there, nailing it, you can get down to what is this equal to. All right, so let's just wait a little bit more for more students to try, and then we will go over it. Okay, great. More students trying. Someone, Gigi posted this in exact form, and also figure out the answer, right? Yeah, in exact form, but in this case, you have to approximate that, right? You have to compute it and approximate that, round it to the nearest whole number, because they are talking about number of days, right? So you should round it to the nearest whole number. I will write as a note. Note, round your answer to the nearest whole number. So note, round your answer to the nearest whole number, okay? Because they are talking about number of days. Number of days, right? So round your answer to the nearest whole number. Okay, so let's do it together, right? If we subtract 1 in both sides of the equation, I'm going to get here minus 1 is 8 equal the 0, 1.5 times natural log of x plus 1, right? Next, one thing I can do is this. I can divide both sides of this equation by this guy, 1.5, right? Let's do that. If I do that, I'm going to end up with the following. This one, but a divided by 1.5, I can do it with my calculator, right? So I'll do it with my Desmos scientific calculator. I get this number. I'm going to work with the approximation, with a good approximation, right? But if it bothers you to work with approximation, you can hit here and you will get the exact value, okay? But in order to show that it's possible to work with approximations, I want to just work with this decimal form, 5.3333. I want to take 3 decimals. That should be enough. And when you work on your homework, guys, also feel free to work with a good approximation or also with the exact form. It will be taken by the system web work, unless, of course, if they say write your answer in exact form, you have to write in exact form. But if not, nothing is said. Try both. The system will take it as long as it's close enough to the answer. 5.333 I want to take, okay? 5.333. I'm rounding this to the nearest 1,000. That should be equal to natural log of x plus 1, right? Then what's next? Notice that here I'm saying that log base e of x plus 1 is equal to 5.333, right? Now, why you say that, Professor, base e? Because this, when you don't see the base next to ln, it means that this base e, the Euler number, right? It's a mathematical agreement. Now I'm going to snail it. Okay? And when you snail it, you will see that this becomes the following in exponential form. After you snail it, this means that e raised to this guy, e raised to 5.333 is equal to the argument of the log, the inside of the log, x plus 1, right? X plus 1. This is it, right? Now I'm going to take my calculator and compute this. Or even better, I can subtract 1 in both sides, right? And say, okay, x is going to be equal to e raised to 5.333 minus 1, right? And then just compute this. That should be it. All right, let's do that. There's my scientific calculator here. E raised to 5.333. Where is e, Professor? Go to functions. You will find it here, e to the x. E raised to 5.333. Come out of there, minus 1. It gives me 206.05. They are asking me for a number of days, right? So I should round it to the nearest whole number. This rounded to the nearest whole number is clearly just 206, right? 206. So let's write that, 206 there, approximating or rounding this to the nearest whole number. So 206. And in the end, as usual, you may attach the units, right? Days, right? Preparation for this best basketball player to achieve these 9 consecutive free throws, right? He has to practice 206 days and each day he practices for 2 hours, I think, right? Yeah, it's written here somewhere. Practices for 2 hours over 206 days. So this should be the final answer. You follow, guys? Try to remember this when you do your special assignment 2, okay? That will come after exam number 2. Okay,